Welcome to Part 2 of our wood frame house construction series. In Part 1, we examined the house plans, the excavation, and the construction of our concrete foundation. In Part 2, we'll move on and look at the framing and weatherproofing systems. We'll look at the framing structures for the walls, floors, ceilings, and roofs, as well as weatherproofing of the roof, window and door openings, and some of the other construction details. To frame our house, we'll use a few different pieces of standard construction material. We'll use a steel I-beam which will support the main floor of our house. We'll use a number of pieces of dimensional lumber, 2x6s and 2x4s for our walls. We'll use sheets of plywood for our floors, for our sheathing in the exterior of the house, as well as for our roof deck. To get started with construction, we'll first construct any of the structural walls that are necessary in the basement. Our house just has a single structural wall, and this wall has several functions. One is to act as a support framework for the stairs, which run approximately down here. Second function is to provide attachment points for posts in this location as well as in this location. And these points will provide structure for the steel beams that run from the far side of the house over toward this post and also from this point to the other side wall. The structural wall will of course also provide support for our floor joists, which will eventually be installed and run across the house like this. And again, that wall provides that sort of support. There may be also some framing done in the basement to create individual rooms, but this is the only wall that actually provides support for the floor above and the roof structures above that. The next phase in the framing process is the installation of the sill plates. And the sill plates are simply pieces of dimensional lumber that are located on top of the foundation wall, and they run around the perimeter. These are used as a location point to help secure the floor joist, which will be installed later. You'll notice all the sill plates are installed using these threaded rods that were placed into the concrete before cured. And these are installed approximately every 4 feet on center, and again they run around the perimeter of the foundation. You'll notice also that there's some chalk lines that have been snapped, and these are simply to help locate the sill plate. On the exterior of the foundation, in this location as well as here, again this is around most of the foundation, this base or shelf is there because it will act as a support for the brick veneer, which will be installed later. Prior to the sill plates being installed, a sill plate gasket, this blue material you see in the photograph, is first applied. And the gasket has a couple of functions. One, it seals the gap between the wood sill and the concrete foundation wall, so that any air can't move between the exterior of the home and the interior. So you don't want to have cold air in the wintertime leaking through that gap or conditioned air in the summertime leaking out. So the sill gasket provides a nice seal between the wood and the concrete foundation wall. The second function is that it acts as a barrier for moisture moving from the concrete to the wood sill. Wood should never be in direct contact with concrete because if it is, moisture that's contained in the concrete could move into the wood. It could cause rot or lead to insect infestation. So the sill gasket prevents any moisture from moving from the concrete into the wood and avoids all those problems. This slide shows a picture of a house that's nearby our case study house. This house is a little different, however. You'll notice that here the sill plates have actually been built up using several layers of material. And the reason for this is to gain additional height in the basement. If you add to the height of the concrete foundation wall, you'll increase the height of your basement ceiling. Standard basement ceiling would be 8 feet tall. In this case, the homeowner likely wanted a higher ceiling in the basement, so they've added to the sill plates. You'll also notice an end plate, which has been added here, and we'll see this also on our case study house in a couple of slides from now. Well, back to our case study house. Here, all of the sill plates have been installed, and the floor joists have been installed as well. You'll notice that all the floor joists have to be supported by structure. So the ends of the floor joists will all be supported by a concrete foundation wall or by a structural wall that goes down to footings below. And that will run all around the perimeter and in the interior. We'll see in an upcoming slide how the floor joists rest also on our steel beam. Also, you'll see some of the end plate material that will be used later on, and we'll see that more clearly in an upcoming slide. In these pictures you can get a better idea of what our floor joists look like. In this house we're using wooden I-beams, and they're called I-beams of course because if you look at this in cross-section this forms the letter I. So these wooden I-beams are set at 16-inch center, so 16 inches between each one of them, And the use of the wooden I-beam as opposed to dimensional lumber, say a comparable 2x10 or 2x12, for example, has a few advantages. The wooden I-beams tend to be a lot more stable. They don't twist and rack and bend as much as dimensional lumber. They're also lighter by weight than the dimensional lumber, so they're easier to install. They're stronger and they can span greater distances, so you can have more open space below. You don't need as many supporting walls to span a greater distance. So that's some advantages in construction. They're easier and faster to install, as well as they allow more open space below. They also provide a great deal of strength, and this helps because they don't flex as much as dimensional lumber, and this might help prevent squeaky floors happening years down the road. The picture on the right, you'll notice that we've got the end plate installed. This has a couple of functions. One, it simply fills the gap between the joists themselves, but also it prevents the joist from tipping over or racking during installation. You'll notice also in this picture, our steel I-beam runs right across here, and the floor joists rest right atop of the beam itself. You'll also notice that on top of the beam there's been a wooden plate installed, and that simply allows for the joist to be attached more easily to the beam. You'll also notice toward the front of the house there's a smaller steel I-beam located there, and the very front of the house is in this location. So this is quite a great distance to span. So the floor joists are supported by the concrete wall here. They're supported by a first steel I-beam in this location, second steel I-beam here, and supported by the concrete wall in the front. So it's quite a great distance that it's spanning. You'll also notice that our steel post or column is right in this location. And while our steel I-beam is very strong, it can't span the entire width of the house without having some support itself. So the purpose of that post is to support the steel I-beam, and that post, of course, is supported by one of the footings that we saw earlier. In these pictures, you can get a better perspective of the steel components in the structure. This is our steel column or jack post, and it rests on a large concrete footing, which we saw being installed earlier if you watched the foundation series, and this would be firmly bolted to the concrete. The top of the post, this is adjustable to get a nice tight fit between the floor and the steel beam, and that would be attached as well, firmly either welded or bolted to the steel beam. The picture on the right, which was actually taken a little bit later on in the construction process, as you can see, because they've begun installing some of the wood framing to finish the basement. This steel beam fits in this pocket, and if you recall from the earlier foundation series, there was a styrofoam block that was placed into the formwork before the concrete was poured, and that styrofoam block created a void, a nice pocket, and a nice shelf for our steel I-beam to fit on. So the steel I-beam is nicely supported directly on the concrete wall, and that weight is directly supported by the footings below. In this picture we can see another perspective of the same steel beam. You can see the shelf that was created on the end wall to support the beam, the post that supports the beam in the center, as well as in the foreground you can see that a post was created using 3 2x6s. So this post would have been specified by the engineer, so 3 2x6s will provide sufficient support for the steel beam itself, as well as all the weight that that beam has to support above. In this picture we can see the plywood subfloor has been installed. And the subfloor is made up of 4x8 sheets of plywood that is 5/8 of an inch thick. This plywood will also have what's called a tongue and groove edge. So the edge of each sheet of plywood has a tongue or a groove, and the groove of one edge of plywood will fit into the tongue of the adjacent sheet of plywood. This makes the joints very strong. The plywood subfloor is held down to the joist, the floor joist, by 2 methods. One is with construction adhesive, so it's glued down, and it's also either nailed by hand or, as we see in this picture, nailed with nails that would be used in a pneumatic nail gun. And the combination of using a tongue and groove edge, using the plywood itself, which is very strong, and gluing it down and nailing it down, will make the floor very strong, and that'll help resist deflection from the weight of furniture that's placed in the room or from people moving around. A stronger subfloor will also help resist things like squeaky floors, because if the floor is very strong, it's less likely it's going to squeak. Also, it'll help avoid things like cracked tiles if there's a finished floor above that is made of tile. If the floor is deflecting because it's not strong enough, you could get cracked tiles or cracked grout lines. In older houses, before plywood was commonly used, you might see the floor, subfloor rather, consisting of 1x6 or 1x8 boards, and those boards often weren't attached to each other very well. They were simply nailed to the floor joist. those boards can move independently and can cause lots of problems with squeaky floors or cracked tiles and the like. In this picture we can get a good view of the completed subfloor as well as some of the other construction details. We notice that a chalk line has now been snapped on the subfloor, and this will simply help locate the exterior walls. We notice that the end plates have been installed, and the end plates are made of a chipboard or a particle board, and this type of material is a little bit less expensive than plywood, and it's also not quite as strong, and it's used in locations where the strength of plywood isn't required. We can also see the sill plate as well as the edge of the sill gasket. The waterproofing membrane, of course, is intact, and we can see the installation of a couple of the window wells. And the window wells are designed to hold back the weight of the soil from the window area when the soil is backfilled. And this is one last view of the completed subfloor, this time looking from the back of the property toward the street. In this picture we can see some of the construction of the exterior walls. This is the front of the house, the front of the garage, looking toward the back of the house. Most exterior walls are built laying flat on the ground, and that's simply because it's easier to do it that way. Once the wall has been completed, it'll then be tipped up into place and secured. In our house, it has 2x6 walls. A lot of the construction you'll see in older houses have 2x4 walls, and the difference between a 2x4 wall and a 2x6 wall isn't so much for the strength. It's because a thicker 2x6 wall will allow for more insulation to be placed and give you greater R value, so better energy efficiency in houses. So most new houses you see built will have 2x6 exterior walls. Most older houses almost exclusively will have 2x4 walls. Interior walls, because we don't have the same issues for heat, will be 2x4 construction. This picture is simply a close-up of a finished wall just prior to being tipped up into place. You'll notice that in the bottom plate a hole has been drilled, and that's simply to accommodate the threaded rod that was placed into the concrete foundation wall earlier. Once the wall is tipped up over the threaded rod, a nut will be placed onto the rod, and that will help secure the exterior wall to the foundation. This is just a street view of some of the construction of the exterior walls. You can see that the walls are built in phases or stages, and the back of the house, you can see that the wall has been complete, as well as some of the sheathing has been added. As well at the front, there's a small wall section where one of the bedrooms is, and you've got the sheathing has been added, and some of the house wrap has been applied as well. In these pictures we can see some of the specialized framing that's necessary to build window or door openings. If you look at the picture on the right, you can see the door has been framed. And if you think about the framing that's required for a door, well, you can imagine that if this door wasn't here, this stud would have continued all the way down to the concrete foundation. Well, if you remove that stud in order to build or construct a door opening, you have to take the load that would have been supported by that stud and distribute it elsewhere. In this case, the load that's supported by this stud, sort of right here, is now supported by a header. And a header would be a 2x8 or 2x10 material depending on the width or span of the opening. And there's often two of them sandwiched together. So the load that would be carried by the header is now distributed or dispersed to the sides, to the right side and to the left side. And that load is in turn picked up by a jack stud, which is that stud that runs just on the interior of the opening, and it goes down to the foundation. There's also a king stud which supplies some support, which goes from the top plate all the way down to the bottom plate. And of course those exist on both sides of the door opening. So any load that has been removed by creating a door opening has to be supported by other means. In this case it's supported by a header and then supported by jack studs and king studs on either side of the opening. If you look at the picture on the left, you see another door opening with another header above. And in the background you can also see a window opening, and it's supported exactly the same way as a door opening would be. The only difference in a window opening is that there's a sill to make up the window sill, and of course that's supported by studs that go below. So anytime you remove framing from a wall, you've got to take the load that would have been supported by that framing and disperse it or send it to other studs, and everything has to go down to the foundation. Framing for the garage door openings is similar to the framing for regular windows and doors, the main difference being the size of the material that has to be used. Because we're spanning such a great distance, we have to use much larger framing material. So instead of using, say, 1 or 2 2x6s, here we've got 3 3x10s sandwiched together, and that gives us enough strength to span this door opening. Also, on either end, there are 2 2x6 jack studs at either point. And again, this gives enough support to support the beam, which in turn supports the load coming down from all of these studs, which in turn will support the roof structure, which will eventually be above. At this stage of construction, the stairs would be installed. Our house just has a single set of stairs running to the basement. And if you recall from previous slides, on the right we have our structural wall, which supports the framing to the foundation, and on the left is a concrete foundation wall. So the stairs in this case would have been pre-manufactured off-site, so they're built in a factory. And that's typical because stairs need to be built very strong, very straight, and very true. And it's much easier to accomplish that if it's built in a climate-controlled environment as opposed to trying to build stairs to meet those qualities on-site where you might be dealing with rain and snow and variations in temperature. So the stairs are installed very early in the construction process, and that simply allows the workers to move freely from the main floor down to the basement. This is a picture of the underside of those same basement stairs, and you can notice that in the construction, a lot of construction adhesive has been used in all the joints. Certainly a lot of fasteners have been used, and by using this many fasteners and glue, it gives the stairs a lot of strength. So you've taken the treads and the risers and you've bound them really tightly to the stringers, and that will allow the stairs to perform very well for all of the loads that it has to support. It will also prevent a lot of the squeaking, and overall just gives it a lot of strength. Once all the exterior framing has been completed, then the attention turns to finishing the interior framing. The interior framing consists of simply building all the walls that will define all the different rooms in the house, the bedrooms and bathrooms and kitchens and so on. In our diagram, we can see that here's a wall that separates the living area, which is in the foreground, to some of the bedrooms and bathrooms in the back. We've got some walls on the side here that separate the actual kitchen area, which is in the foreground, to the living area and so on. So at this point during the construction, you can get a very good idea of what the house will look like and how it will function as a house. In these pictures, we see a different house being framed. This is a row house or townhouse, which is being built nearby our case study house. Now, a row house like this would be framed exactly the same way as our single-family house. One of the main differences, however, is you'll notice in both pictures there is the existence of a concrete block wall. And this concrete block wall separates the suite on this side, which will be built, to the suite on this side. So this is a multi-family unit. The purpose of the concrete block wall simply acts as a fire stop. Concrete block walls have a much greater resistance to fire than, say, a 2x4 wall that's simply made of drywall. That concrete block wall allows the homeowners, if there was a fire, to get out safely, and it gives them more time to get out safely and helps prevent the spread of fire. So hopefully the fire department would arrive and be able to put out the fire in one unit before it spread to the next. Well, if we go back to our case study house, once the exterior and interior walls have been framed, the next stage would be the construction of the roof. Now, the roof can be built a couple of different ways. It could be what we call stick-framed, which means simply built from individual pieces of lumber nailed together, or it can be built using trusses. In our case, we'll use trusses. The picture you see in front of you is a bundle of trusses that have been delivered to the site. It looks like a bit of a mess here, but the individual trusses are actually built off-site and they're engineered to very exacting standards. Trusses allow for a very strong and lightweight roof, and that allows the roof to be built much more quickly. And we'll see that in more detail as we look at the next couple of slides. The pictures on the right are simply some of the metal fasteners that will be used to attach the trusses to the roof. And again, we'll see that in some upcoming slides. In these pictures, we can see that some of the trusses have been separated from the pile that we saw a moment ago. And the picture on the right, you can get a little bit of an idea of what the truss looks like. So you can see the top cord gives you the shape of the roof. This is the peak of the roof here. The bottom cord would define the ceiling height in each one of the individual rooms. And some of these pieces here, this lateral bracing or webbing, would be the interior part of the truss, which would give it its strength. And the picture on the left, there's a bit of a pile here, but you can also make out that in this truss, this is the roof peak. That's the peak of the roof right there. And when they're assembled, as we see in the next couple of slides, you'll start to see how these create the shape of the roof and allow for really quick installation. From another project near our case study house, we can see that a crane is on site and it's lifting the trusses into place. Using a crane for all of the heavy lifting makes pretty short work of the truss installation, and all the workers really have to do is secure the trusses to the wall frames and secure the trusses to each other. A house like this could be done without a crane, but it would take much longer. Using a crane, this kind of installation would probably take less than a day to complete the roof structure. If we go back to our case study house, you can see that the truss installation is pretty much complete. While from this angle it looks like a fairly complicated array of trusses, if you look carefully you can start to see how the different trusses define the roof shape. You can see at the front of the house the truss starts to form the first gable wall here, and there's a ridge beam that goes along here. We can of course see the same thing, the same shape in the garage a little more clearly, and again how the ridge in the garage is defined. And also in the back of the house, if you look very carefully, you can start to see another roof line here, and this is the ridge line that goes in the back of the house. So from this angle you can start to see how the trusses work together to give you the overall shape of the roof. And we'll see that more clearly and in more detail in some upcoming slides. This is just another picture of the trusses from the front of the house, this time from a little bit different angle. This angle affords us a little better view of that ridge line that's formed by the peak of the trusses in this location. So that becomes a little more clear in this picture. Now I mentioned a moment ago that an alternative to using trusses to frame the roof structure is to use stick framing, or the stick method. And that it simply means that the roof is framed with individual pieces of lumber. And in these pictures, the next several pictures, is a house in our neighborhood that's done by this method. So you can see here that some of the roof structures started to be framed using these joists. The picture on the right is probably a better example of the same picture. So these joists are installed, and the roof will be attached, or the ceiling rather, will be attached to the underside of these joists. And these joists form part of the roof structure. In this case, they end in a beam and are held together by metal brackets. So this will be part of the roof structure. The ceiling will be attached to this, and this is all done individually, so nothing's prefabricated off-site beforehand. In these pictures we can see more of the roof framing. On the picture on the right we can see more of the joists have been added, and these will help define the roof structure, and these extend from the front wall to an interior load-bearing wall and then continue on toward the back of the house. The picture on the left is just kind of an interesting picture. This is a cut list, so one of the framers or roofers has developed a cut list which will indicate how many pieces of 2x6 material, how many pieces of 2x8s and 2x10s will be needed. And you can see by just this list there's over 100 different pieces of material that need to be handled, that need to be cut and attached individually. So you start to get a sense that stick framing a roof is a much longer and more tedious process, and it also leads to more waste on site. These pictures show more progress in the roof framing. The picture on the left, you can see that all of the joists have been installed and they're ready for some of the roof framing to continue. The picture on the right was taken just shortly afterwards, and it shows some of the framing in place. Stick framing usually starts with installation of these ridge beams, and this defines the actual structure of the roof, but more importantly indicates exactly how long each individual rafter has to be cut in order to be installed correctly. In these pictures we see more progress on the roof framing. In the picture on the left we can see how the original outline of the roof is first constructed before all the rafters are filled in. In the picture on the left you can see that more of the roof has been completed. You notice a few things in this picture. One, you can see that the soffits have been created as well, or soffit ladders using a little bit different construction technique. We notice some of the roof framing some of the roof sheathing rather, has also been installed. That'll help give some structural rigidity to the roof until it's completed. You'll notice also that blocking has been placed between the rafters, and that helps fill the space between the top plate and the rafters. And you'll also notice at the back of the house here, they actually are using truss. So in this house they're using a combination of pre-built trusses and stick framing. And that's not uncommon. Trusses have pros and cons to them as the stick framing, so sometimes it's an issue of design or cost or just preference of the builder. Sometimes you'll see trusses being used for certain applications and stick framing for other applications, so that's not uncommon. Here are two more pictures of the same house being framed. On the picture on the left you get a little better idea of what the odd-shaped truss that's being installed looks like. And in the picture on the right you can see that the stick framing is also continuing. So these pictures give you a good idea of how stick framing and truss framing can be used together. And these are two final pictures of the same house again. Here the roof framing is nearing completion, so you can see the sheathing has been added, and it'll be ready for shingles very shortly. Well, back to our case study house, we can see that the trusses have been installed and the sheathing has been completed as well. So at this point we're ready to turn our attention to the rest of the roof system, so the underlayment and the shingles and so on. So in the next few slides we'll look at some of the details and construction techniques that are used to make sure the roof is waterproof and weathertight. In the next few slides we'll look at some of the weatherproofing systems for the roof. So we'll look at some of the different elements, such as how flashing is installed around chimneys and other openings in the roof. We'll look at how venting systems have to work. We'll look at some of the elements that go into assembling a roof. We've seen this sheathing already being installed. We'll look at building paper or some of the felt that's used, as well as some of the additional waterproofing materials that are used around the eaves. So we have to understand that in order to make a roof watertight and weatherproof, all these different elements have to work together as a system, and we'll see those in the upcoming slides. The type of weatherproofing system that's used on a roof will depend considerably on the style of the roof. The most common styles that we see are a gable roof and a hip roof, and these two different styles are often used in combination. And these kinds of roofs we'll often see underlayment used, some kind of builder's paper, and then your standard 3-tab shingle over top. So those are probably the most common two types of roof styles that we see. Other styles that you see from time to time, such as a shed style or a flat roof. In a shed style, this is simply a single plain roof. If the slope is steep enough, it's possible to have shingles, but there might be some kind of membrane system used on that roof. A flat roof is similar to a shed roof, except that the slope is much less. Most flat roofs aren't perfectly flat. There is some slope to the roof, and that slope is designed to allow water to move to drainage or to scuppers and released from the top of the roof. So those roofs that are flat aren't really flat. There is some slope to them. Other styles of roof, like a butterfly style, these are pretty rare. You might see these in modern home styles, or where the architecture has specified a certain roof type to coexist or to go nicely with the style of house that they're developed. This is really a flat roof style. In other words, you couldn't use shingles on a roof like this. You'd have to use some kind of membrane, either a torched-on membrane or a rubberized membrane. One of the problems with this kind of roof, as you can imagine, if you have snow load that builds up on top of the roof, well, all that snow is going to end up in this valley. So you could potentially get a lot of weight from snow and water and potentially a weak spot. So this isn't probably the best kind of roof style for northern climates, where we have to deal with lots of rain and snow loads and so on. Other styles of roof, there's a combination style here, and this is really just a style where you have two different slopes. The slope here might be a greater slope, say 8 and 12, and it might transition to a shallower slope, 4 and 12. This is relatively rare as a single house style, but you might see elements of two different slopes in a roof in a regular house. As long as the slopes were sufficient, you might see shingles used. If the slope was shallow enough that shingles couldn't be used, say less than a 4 and 12 pitch, then you'd have to have some kind of membrane system installed. Mansard roofs up at the top here, these are relatively uncommon. You do see them from time to time. And a mansard roof is simply a roof where it has a relatively flat top part and then a slope on the edge. So you may see shingles used around the edge where the slope is more steep, and some kind of flat roof material, again a membrane material, used on the top part. The last style that we see here is a gambrel roof, and this is a style that we most commonly associate with barns. It's a style that's used to increase the volume of space inside the barn, and that would be used for storing hay or whatever materials that the farmer had to store. A gambrel roof is simply a roof that has two different slopes, a shallow slope on the top and a steep slope here, and often we see metal roofs used for these kinds of roofs. So depending on the type of roof, depending on how the roof systems are joined together, different slopes and so on, that will vary the type of weatherproofing and materials that need to be used to ensure that roof stays weathertight. So if we return to our case study house, we can see that it has a combination of hip and gable style roofs. The gable roofs are defined by this section here, as well as a nested gable in front. The garage also forms a gable roof. If we look at the picture on the right, we can see the house also has a hip roof, and the hip roof is defined by this ridge beam here, as well as a hip on either side of the house. And this is pretty typical in house construction, to use combinations of hip and gable style roofs. In this slide we see a cross-section diagram of our roof. And this diagram gives the builder some information about the different materials that are being used as well as their application. So we're given information on the roof trusses. We're told the roof trusses will be used and they'll be installed to 24 inches on center. Insulation in the attic will be R40, and that'll be blown-in insulation. We're given some information about venting. The venting toward the ridge will be applied every third truss. We're also told that there'll be asphalt shingles will be used, and those will be applied on top of 15-pound builder's felt. That will all be applied on top of sheathing, which we saw in some of the earlier slides. We're given some information about the eave protection, and this refers to a waterproofing membrane or underlayment that will be applied from approximately the edge of the roof up about 48 inches to about this location, and this will provide additional protection for water penetration, particularly as it relates to ice damming. We're also given some information about some aluminum edge flashing that's applied right at the edge here, and that's simply to ensure that water that flows down the shingles will not wrap up and get underneath the edge of the shingle and damage any of the wood. We're also told that there'll be a vinyl soffit material, and this is where the vent will be. So the air will enter in the vent here, it'll move through the attic and move all the way out through the vents at the top of the roof, and this will ensure that the attic is well ventilated, so any moisture or condensation that gets into the attic will be easily removed. The next few slides show a picture of a house in the neighborhood. It's not our case study house. These slides show pictures of the ventilation. And in order for ventilation to work properly, so in order for the attic to be properly ventilated, really requires two elements. It requires air to be able to get into the attic space, and as we saw that in the previous slide, there's often an air inlet in the soffit, so air will move in from the soffit, move up the attic space, all the way up, and eventually be exhausted through the ridge vents. So you always have air moving from a lower point to a higher point, and as warmer air rises, it's naturally pulled out of the attic. Now, it's important to ventilate attics for a couple of reasons. One is that if moisture gets into the attic space, it needs to be removed. Now, moisture can lead to rot, it can lead to mold growth, and too much moisture can actually degrade the insulation if the insulation gets wet. So proper ventilation is important. Now, ventilation is determined by a formula generally related to the size of the house, the size of the volume of the air that needs to be ventilated. The larger the house, the more vents it would have. Now, if a house doesn't have enough venting, that means not enough of that air is being moved out of the attic. That's when moisture problems can occur. If a house has too much venting, if too much air is being pulled out of the attic, that can be a problem as well. If too much air is being pulled out of the attic, that might create a slight vacuum in the attic, and that might cause some of the conditioned air from the house below to be drawn into the attic from cracks in the ceiling, recessed light fixtures, or hatches that would lead to the attic. If that's the case, a lot of that conditioned air would be wasted, so it would be inefficient, but also that warm conditioned air would contain moisture and lead to some of the moisture problems I mentioned a moment ago. In this slide, we can see that the shingling has begun and the roof is partially completed. The bundled shingles are brought to the roof peak and stored up on top. That's simply to make it easier for the workers to access the shingles. We can also see that some felt paper has been added to the valleys as well as along the eave, as those locations are particularly prone to water leakage. In this close-up, we can see a couple of important details as it relates to roof flashing. First thing we notice is that we've got flashing that goes along all the edges of the roof. And this is drip edge. And the purpose of drip edge is that any water that hits a shingle and runs toward the edge of the shingle, it won't roll underneath the shingle and get the wood wet. It'll roll off the shingle, it'll hit the drip edge, and then it will then drip down into the eaves trough. So there'll be an eaves trough located down here. Now typically there isn't bare wood here. This would be covered with metal fascia as well. So any water that rolled off the roof would hit the drip edge or hit the fascia and then end up in the eaves trough, and then be funneled out to a downspout and off the site. The second element, we see these metal pieces along here, and this is step flashing. And step flashing is used wherever a sloped roof surface meets a vertical wall surface. And the way that step flashing works is each successive shingle has a piece of flashing underneath it. So you can't see it very well in this picture, but step flashing actually is L-shaped. So the top of the L would meet the wall, and the horizontal part would meet a shingle. So a piece of step flashing is installed, then a shingle, another piece of step flashing, then a shingle, and it's done that way all the way up the wall, so that the step flashing and shingles are stepped or layered, so that any water that might get under a shingle would hit a piece of flashing and would drain onto the next shingle and so forth down the wall. And this prevents water from getting underneath shingles and is used in all kinds of locations, particularly where vertical wall surfaces meet the sloped roof surface. Here we can see the roof has been completed, all the shingles have been installed. You can also see that all the individual vents at the ridge have been installed, so that's complete. And we also see the installation of a skylight which has been installed and properly flashed as well, and that'll bring some nice daylight into the house. You'll also see one or more of these plastic pipes that protrude through the roof surface, and these are vents for the plumbing fixtures. So these are vents, but they have nothing to do with the attic vents, but have everything to do with the plumbing vents. And we'll look at the plumbing fixtures and the venting requirements in a later series. If we check back on the progress of our case study house, we can see that the roof here has also been completed. The shingles have been installed, all the flashing's been installed, so at this point, if there's any rain, the house will remain dry inside. Once we reach that stage of construction, we're ready for the installation of doors and windows. So in our case study house, the doors and windows have been installed, and door and window installation is relatively straightforward. Door assemblies and window assemblies are typically built in a factory, delivered to the site, slid into the opening and secured. In the picture on the left, we can see that our front door has been installed, and this is installed in front of our porch. There'll eventually be fill in this area, and then concrete will be poured on top. So the door is simply slid into the opening and secured. In the picture on the right, you can see one of the windows that's been installed, and the installation techniques will vary depending on the kind of window that it is. Windows can be made of aluminum, wood, fiberglass, or in our case vinyl. And each different window type may have some different installation techniques. So there isn't one single technique that will work for all different windows. The main components though are the window needs to be square and plumb, secured to the framing, and also the flashing has to be installed such that the window won't leak. So in our case we've got vinyl windows, and even though this window is 4 separate panes of glass, this would have been built as a single unit in the factory. When it's delivered to the site, the opening would have been preformed, the window slid into the opening, and secured by screws. This slide shows several pictures of a window being installed in a neighboring property. This installation technique is a little bit different from the windows in our property. This window is a vinyl window, like we have in our house, but it's installed using a metal nailing flange. So there's an aluminum flange that runs around the window. And the window is installed simply by nailing through the holes in the flange and securing the window directly to the wood framing behind the sheathing. You'll notice that some special attention has been paid to the layers of material. We've got our house wrap that acts as an air barrier, and it's tucked behind the window and wrapped around the inside of the window opening. You've also got some black waterproofing material which is also wrapped inside the window opening and is then wrapped outside, and the window itself is placed on top of that. So this careful layering of materials will help with waterproofing. These pictures show the installation of a window, this time from the inside. You notice that the waterproofing material we saw on the outside is wrapped around the inside of the window opening. We saw that a moment ago. You'll notice also that it's important for windows to be installed such that they're level and plumb. So shims are often used under the structural parts of the window. So you'll see the shims used under these parts of the window to make sure the window is level and plumb. Now, it needs to be level and plumb, partly so the window will look right, but also more importantly, if you have an operable part of the window, we have a casement window here, so this window swings out, that if the window was racked or wasn't straight, that window opening might not function properly. The window might get stuck and not open as easily as it should. So it's important for windows to be shimmed so that they're level and plumb. Now you'll also notice there's a large gap here at the bottom and also at the top and the sides of the window. This gap is usually filled by expanding spray foam insulation. The spray foam insulation has several functions. One, it's very sticky, so it actually helps adhere the window to the opening, but more importantly it helps with air infiltration, so it prevents any air from infiltrating, and because it's foam it also has a pretty good R value, so it'll give some thermal resistance as well, so the window will be warmer and you won't have any drafts in the inside. In the last couple of slides in this series, we'll have a look at the house wrap or air barrier that's been installed on the house. If we first look at the cross-section of our wall diagram, we'll see where the house wrap is located. So this diagram shows us the buildup of the wall from the outside to the inside. And of course, we start with the brick facing, and our house will have a brick facing all around it. Just interior of that is the house wrap. So that's what we'll have a look at. This drawing also gives us the details on the plywood sheathing and our 2x6 wood studs, R20 batt insulation and vapor barrier rather, and so on. And we'll see all of these in the finishing section coming up. But for now, we'll have a look at the house wrap and how it's installed. In these pictures, as well as some of the previous photos, we've seen the installation of the house wrap. Now, house wrap has a variety of functions, but its primary function is to act as an air barrier. So it prevents the movement of air from the exterior to the interior. That helps prevent drafts and makes the house more efficient. Now, there's a number of different types of house wrap. They go by different brand names depending on where it was purchased, or the distributor, or the manufacturer. And some of them have slightly different qualities, but they're all generally designed to prevent the movement of air. Now, some of the house wraps will also have some moisture qualities. They may allow any moisture vapor that's inside the house or has been captured somehow to move through the barrier, but it won't allow any moisture or liquid water to penetrate. So they may have some of those qualities as well. And those vary a little bit depending on the exact kind of material that's used. Now, most people who have seen houses built from several decades ago would have seen builder's paper used. So that black felt paper, it comes in 4-foot rolls and simply rolled around the house. That's used as an air barrier. And that worked for many years reasonably well. It did have some limitations. It would break down over time, particularly if it did get wet. And because it came in 4-foot rolls, there were lots of seams. And anytime there's a seam, there's an opportunity for air to penetrate and get through. So you don't see builder's paper used very much as an air barrier. You typically see house wrap used. That's what's used in our house. House wrap comes usually in 8-foot rolls, so it's easy to roll out, it's easy to apply, it's stapled to the sheathing. And because it's in 8-foot rolls, there aren't very many seams. So it's a much more effective material at preventing the movement of air. In this picture, we can see that the house wrap has been completely installed. It's wrapped all the way around the house through all the nooks and crannies and pulled tightly into all the corners. You can also see that wherever there is a seam, some special red tape has been used. It's very sticky, and this will prevent any air leakage between the seams. So all the seams are taped, and all the windows and door openings are sealed properly, so this house is as tight as it could be in terms of air movement. So let's return one more time to our case study house. We can see that in this picture, the house wrap has been installed and all the seams have been taped. So we've got our roof on, it's weathertight, we've got our windows and doors in. We generally refer to this stage of construction as a lock-up stage. So we can generally secure the inside of the house. So now we're ready for the next stage of construction, and that would be the mechanical systems, which would include electrical, plumbing, and HVAC, and those types of systems. And we'll have a look at those in greater detail in the next series.